Hello everyone and welcome back. In the last episode, we introduced what dynamical systems are, and today we are going to consider three concrete examples. In studying systems theory, which is a very difficult subject, it is important to consider real examples, tangible examples, in order to understand the concepts around systems better. What we are going to consider is how a simple physics problem turns into a differential equations, then into state equations, and finally we'll understand the fundamental difference between linear and nonlinear systems, and between dynamic and static systems. So let's jump right into it. The first example we are going to consider is the cart on rails. We are going to consider a cart that is on a frictionless plane that is moved by a force. There, the cart is with mass m and is sliding on the rails with no friction. The force F that depends on time acts on it. It is directed along the direction of motion, and thus, since it depends on time, it's not a constant force. Now, what does physics tell us about this situation? The good old Newton's law tells us that mass times acceleration equals the force that acts on the subject, on the system. This is very simple, no? But the thing is that in order to write it in a form that's useful for analysis, we're going to need to introduce three related quantities. The first quantity is the cart's position. The second quantity is its velocity, that is going to be considered as the derivative of the position in time. And then we have finally the acceleration. The acceleration is going to be considered as the derivative of velocity, and thus it's going to be a second order derivative of the cart's position. Finally, substituting these considerations into Newton's law, we get that mass times second order derivative of position equals the force. Or equivalently, if we consider on the second derivative of position, we are going to have the second derivative of position equals 1 divided by m times the force. And this is the first important observation. This is already a differential equation. It is linear, it has constant coefficients, since we know the mass, and we are going to consider that we know. And it is second order. And this is no coincidence, because we are going to see this pattern come up again and again in systems theory. The second example we are going to consider is a cart with a spring and a damper. So we are going to make it a little bit more complex. Now, our cart is connected to a wall through two elements. We have the spring, which is an elastic spring with an elastic constant K, and then a damper that's going to present some viscous friction with a constant C. The parameters M, K, and C are numbers that characterize our physical system, and they have natural constraints. Mass cannot be zero or negative, and also K and C can't be negative, so they can be equal or greater than zero. One important detail is that we measure position relative to the spring's resting position, so it is relative to the point where the spring exerts no force at all. Now let's write the force balance on the cart. There's still the external force F of t, but now we add the spring's restoring force proportional to displacement, the negative sign, and the viscous friction force proportional to velocity, also negative, because these two forces need to oppose movement. Now rearranging, we get the standard form. Now again, we have a linear constant coefficient differential equation. But now we also have present a first order term, thanks to the friction. And we can notice that if we put C and K equal to 0, we get the equation that we had in the previous case with the free cart. So far, we have a single second order equation, but in systems theory, there's an alternative that is extremely powerful way to represent the same system, and it is through straight state equations. The idea is this. Instead of working with a second order equation, we turn it into two first order equations by introducing two state variables. x1, that is going to be the position, and x2 that is going to be velocity. Now, considering the physics, the definitions that we have, it follows automatically that x1 derivative in time equals x2. And from our earlier equation, we get this second one, which is the derivative of x2 equals minus k divided by m x1 minus c divided by m x2 plus 1 divided by m ut. Now here we have called ut the system's input, which is nothing other than our force, f of t. If we choose position as the output, we simply add that y of t is equal to x1 of t. Now, this is a set of first order linear differential equations, and is what we call from now on the state equations. It can be written in extremely compact form through matrix form. This form will come up constantly throughout this course, so it's important to get comfortable with it right from the start. This exact same system can also be represented through its transfer function. It's important to keep in mind that differential equations, state equations, transfer functions are three different ways of describing the exact same system. They are not different systems. There are three different languages, we can say, that are telling the same story. But how realistic is this model, really? Before moving on, let's stop for a moment and be self-critical. This cart with spring and damper model is linear, yes, but only under the assumptions that we made, and those assumptions have limits. For example, the model is valid only for small displacements. For large values of p of t, unmodeled non-linearities or even discontinuities could show up. The parameters m, k, and c that we have used might be known with error. So we have, in this case, in the model that we have just built, parametric uncertainty. There can also be unmodeled disturbances acting on the real system. The takeaway here is simple but fundamental. All models are always approximate models, no exception. Finally, let's consider a third example. This is going to be our first nonlinear example. The tank with a hole. So let's switch to a different physical setting. Let's imagine a water tank with an inflow rate that we are going to call P of T, which we can manipulate at will. And this is our control input. Then let's say we have a hole at the bottom of cross-section E through which water flows at a rate, let's call it L of T. And then we have the height of the water column in the tank. The key question here is, how does the outflow rate depend on the level h of t? We use a little physics trick. The energy balance of a single water particle of mass m about to exit through the hole, its potential energy converts into kinetic energy. And so the outflow rate is L of t equals E times velocity. So it's going to be E times the square root of 2gh of t. Now let's write the flow balance in the tank. The change in the water volume in the tank equals what comes in minus what comes out. So let's say that the change in volume, the volume is going to be the surface of the cylinder of the tank that we are considering, times the height, is going to be equal to what comes in minus what comes out. What comes in still remains P of T, and what comes out is what we have just defined. And the derivative in time of the height of the cylinder is going to be equal to what comes in minus what comes out, because this is no longer a linear equation, since we have the square root over h of t. This is our first example of nonlinear system. Depending on what we're interested in observing, we can choose as output the height, so the level of the tank, or we can choose the outflow rate, the L of t. So what is important on this lesson? The first take is that the evolution of a system's outputs always depends on two things: the inputs we apply and the system's initial conditions. This depends on initial conditions. The fact that the system remembers where it started even with zero input is exactly what defines a dynamic system, distinguishing it from a purely algebraic system. And the second take is that if we consider a system which output can simply be k times the input in time, this is not a differential equation, so it has no memory of the past. The output depends instantaneously on the input, and this is not a dynamic system. It's a purely algebraic static system. Here's the fundamental distinction to take away from this video, which is that a system is dynamic when it has memory, when its future depends on where it currently stands, not just on what input I'm feeding it at that instant. And in the next video, we'll see how to solve these state equations and what the behavior of a linear system over time actually looks like. And if you found this video useful, hit like and subscribe to the channel. Let me know in the comments if any step wasn't clear. I'll answer to everyone.